hurricanes, earthquakes, drought, tsunamis, floods. Since ancient times to present day, extreme weather, depletion of resources, and natural hazards have challenged communities all over the world. With global climate change adding new uncertainties to the power and frequency of these events, we now face one of the greatest challenges in human history, a challenge that will test our intellect, our fortitude, and our ability to unite behind a common cause. The question is, how will humanity respond to such a rapidly changing world? The answer lies not only in adaptation, but in developing new tools to help us understand the Earth's atmosphere, lithosphere, hydrosphere, cryosphere, and biosphere as a single connected system. Imagine living in a world where we could better predict, prepare for, and respond to catastrophic events. For more than 50 years, NASA has studied our home planet from space, in the air, and on the ground to answer fundamental science questions about the changes we see in climate, weather, and natural hazards. The next 20 years will see a revolution in Earth science. Emerging technologies will enable new measurements to reveal the complex interactions among Earth's natural systems. Observations will be more efficient and models improved for forecasting weather, climate, and natural hazards. This knowledge will help us better understand and assess hurricanes, earthquakes, and climate change. It will lead to practical applications that improve our quality of life. Today, NASA gathers critical data by flying multiple spacecraft around the Earth. In the future, we will have many more distributed observations. Underwater capabilities will look at ocean circulation, currents, ocean temperatures, and salinity. UAVs, or uninhabited aerial vehicles, will validate and augment the data captured in space. New LiDAR instruments will measure 3D winds, cloud heights, and ocean turbulence, as well as vegetation, canopy heights, and surface topography. Space-based radar will be able to monitor changes in stress on the major earthquake faults, as well as soil moisture and cloud dynamics. And other systems, such as radiometers and spectrometers, will provide global measurements of Earth's atmosphere, land, and oceans with unprecedented resolution. Hundreds of small satellites, flying in formation or maneuvering with respect to one another, will track time-critical events and could simulate a large aperture for very high-resolution measurements without a large satellite. High-resolution ensemble models will enable us to better predict the severity of storms and the best and worst-case scenarios. We'll be able to more accurately forecast how much rain will fall and when, farther into the future. And we'll be able to observe and even anticipate earthquakes, volcanic eruptions, and tsunamis. Formation-flying satellites will have the ability to reconfigure on the fly to watch these events evolve. Constellations of complementary satellites with different capabilities will work together autonomously. That means if one satellite fails, another will be able to replace or repair it. Multiple spacecraft will provide a web of Earth observing instruments in space to exchange information, to command one another, and download data to scientists, decision makers, and first responders in a timely manner. Different vantage points will provide vertically and horizontally resolved measurements. Geosynchronous satellites 22,000 miles above the equator will match the Earth's longitudinal rotation to provide continuous observations of the same regions. High-resolution optical and infrared sensors will be placed in stable orbits at the Lagrange points, an orbit between the Earth and Sun, which is approximately 1 million miles from Earth. These sensors will allow measurements of variables like clouds, water vapor, ozone, and aerosols under constant sunlit conditions over broad geographic areas. All this additional data will require large-scale, exascale computers to solve billions of operations per second. These computers, coupled with various types of models, will allow us to visualize and understand the interactions among Earth's systems. Complementary and comparative measurements will provide global, regional, and local scale data products. NASA won't do this alone. Many Earth-observing missions will rely on the cooperation of other agencies, private industry, and multiple nations, with scientists and technologists working in multiple disciplines. When the data is shared and compiled among the international community, it will allow us to better observe, understand, and respond. This is our vision for the future, a vision that harnesses the most advanced science and technology to better understand our planet and improve the quality of our lives.